Hi, thank you for taking your time for my session, Productionizing ML with ML Ops and Cloud AI. I'm Sato, developer advocate from Google Cloud team. In this session, I'd like to cover these topics. First, I will discuss what is ML Ops and how you can build a scalable machine learning development platform with Cloud AI. Then I will discuss what are the gaps between the POC and production and how to fill those gaps. And then I will discuss why the data and the model validation is important and how you can do that. Lastly, I'd like to explain how you can build a machine learning lifecycle management pipeline. So what is ML Ops? I started discussing about ML Ops like 2 or 3 years ago after hearing this word from one of the senior software engineers in Google. He said, launching the machine learning system is the easiest part. The hardest part is keep operating that for many years. The real problems with the ML system will be found while you are continuously operating it for the long term. So we thought that many practices from the DevOps can be applied to machine learning problems. What is DevOps? DevOps is a practice used in the software engineering. It's all about unifying software development and software operation by advocating automation and monitoring at all steps of the software construction, integration, testing, and releasing. So we can use the same practice for building a production machine learning system. That is ML Ops. So it's all about unifying machine learning development and the machine learning system operation by advocating automation and monitoring at all steps of the machine learning pipeline. So with that practice, ML Ops practice, you can start building your production-ready, scalable machine learning development platform. To avoid anti-pattern like this, depending on an ML superhero. I've seen many ML superheroes in my customers and clients. They can be an ML researcher who reads the very complex paper from the academics for the machine learning and data science. But they also can be a data engineer who can use the Hadoop or maybe BigQuery or data warehouses to implement the large-scale pre-processing. And also, this ML superhero can be an infra and ops engineer as well for the production system, because they can do everything, writing Python code, Go code, Java code to build the infrastructure. And also, they can be a product manager if requested. They can write the production specification documents and talk to their partners, talk to the executives or business stakeholders and explain what is this product, what benefit the AI or machine learning can bring. And they can do that from POC to production. So this ML superhero is a great person, but it doesn't scale for enterprises or large organizations. Because in large organizations, there could be like tens or hundreds of different machine learning or AI production projects that should be covered by the superheroes. And there's no tens of hundreds of superheroes. So how to solve this problem? So it's very important to build a scalable machine learning or AI team with the multiple different roles, starting from data engineers and data scientists, ML engineers, developers, and business analysts, so that the teams can be scalable and should not be dependent on a specific superhero person. And also by splitting the role, you can split the responsibility to multiple roles. For example, data engineer should be responsible for ingesting data from data warehouses. And also, data engineer can write some code for preparing and pre-processing the training data at scale. Whereas the data scientist can focusing on designing the machine learning model, neural network, or the random forest and everything to get higher accuracy working with the stakeholders and the other roles, like ML engineers or data engineers, so that data scientists can pass the result, the design, machine learning, the models, and so on, to the ops engineer. Ops engineer can be responsible for training the data at scale for the production system, or the ops engineer can build an infrastructure for the production quality, data validation, and also model analytics, and deploy it, push it to the infrastructure at scale. So this is where we may want to think about how you can build a scalable and production-ready machine learning platform that can be shared with the multiple roles, especially with the data scientists and ops team. The solution could be a cloud service. And this is the reason why we provide multiple components within the umbrella of the AI platform. So the product called AI platform consists of the many different components and modules, such as the deep learning VM, or notebooks, or Kubeflow pipelines, training and prediction infrastructure, and so on. And the modules or components of the AI platform can be easily integrated with the other data products, such as BigQuery, Dataflow, Dataproc, Dataproc, and Data Studio. So that by using the Cloud AI and Google Cloud Platform, it's so easy for the ops team and also the data scientist teams to build a scalable and production-ready machine learning development platform. And there's another product I want to introduce, which is TensorFlow Enterprise. TensorFlow Enterprise is all about productionizing TensorFlow with the power of Google Cloud. So to explain what's the benefit of the TensorFlow Enterprise, we think about some scenarios between the data scientists and the ops team. For example, data scientists may ask the ops teams to get a new PC for the machine learning development. Maybe everything is installed maybe by noon, because he have to finish his the training tasks within a couple of days. But ops teams wonder why they need so many GPU machines, expensive, powerful GPU machines that would cost like millions of dollars if they have like multiple GPUs. Are they really used at the high efficiency? Or maybe some of the data scientists will not use GPUs anymore after launching the product. So these are the challenges when you want to scaling out the development platform of the machine learning systems. So in the early stages, data scientists would order the new GPU machines as the on-premise GPU server, but usually it takes a couple of weeks and they are expensive machines. And also in early days, data scientists would spend their times for installing the softwares, the CUDA, TensorFlow, NumPy, Matplotlib, and so on by themselves. But those kind of homebrew development platform cannot be scalable as the operation, because you would have the problem of the over-provisioning to GPU problems. Maybe one data scientist would need much powerful GPUs right now, but the other data scientists would forget about the GPU servers because they finished launching the product. And they could not get any tech support. In early days, data scientists used to spend like half a day or maybe a couple of days just for fixing the driver issue, not the data science issues. So the one solution we can bring is the TensorFlow Enterprise, specifically deep learning VM. Deep learning VM or DLVM is a standardized VM image for data scientists that supports the TensorFlow 1.15 and 2.1, and now it's supposed to 2.3 as well. It has the everyday tools of data scientists, starting from the CUDA drivers, NumPy, scikit-learn, Jupyter, everything already installed in the VM images. So you don't have to install everything from scratch. And because it can be used as a standardized VM image for an enterprise, it can be easily managed and supported by the ops team, rather than supporting any arbitrary software stacks installed by the data scientists. And also, deep learning VM or DLVM can be easily deployable with Google Cloud. It can be used as a VM with Compute Engine or Air Platform Notebook and other computing platform on Google Cloud. And because it's a cloud platform, you don't see any provisioning problems. If you want to use like 8 GPUs, you can just create an instance with 8 GPUs. And once you finish your work, you can just stop the instance, shut down the instance. So you don't have to pay any unnecessary cost for the GPUs. And also, you can even get some other options, such as the preemptible GPUs. Preemptible GPUs provides much higher cost efficiency compared with the proper GPUs. And the preemptible GPUs may have the lower priority compared with the standard GPUs, but the cost is almost 1/3 of the standard GPUs. So you can have the like 3 times more tasks running on GPUs with the same cost. And also you can get the other options such as Tensor Processing Unit or TPUs that also provides much higher cost efficiency compared with the standard GPUs. Let's take a look at some video of the demonstration of the TensorFlow Enterprise. So you can go to the Compute Engine VM instance, the console, and look for a deep learning VM so that you can easily choose the TFDV image to create an instance of the Compute Engine. You can specify any number of the CPUs, or you can choose any GPUs you want to use. And lastly, you can specify the version number of the TensorFlow Enterprise and click the deploy and wait for a couple of minutes, and that's it. You don't have to spend a half a day to install the CUDA drivers and TensorFlow and scikit-learn and so on. Then another product I'd like to introduce here is the AI platform training. This is a module for training the model with the managed infrastructure running on the Google Cloud. And the AI platform training already installed with all the tools for the data scientists, so you don't have to install everything from scratch. And also the hardest part for the large scale training is the distributed training. This requires another set of the skills for building a distributed cluster with GPUs and TPUs. But with AI platform training, you don't have to care about that. You can just submit your job to the training so that it can be run with the multiple GPU nodes, not only with like a 4 or 8 GPUs, but also that could be run with the like tens of GPUs, maybe even hundreds of GPUs. Also, you can get the state-of-the-art and automated hyperparameter tuner developed by Google, so that you don't have to install and set up your own hyperparameter tuning with the open source tools. So that was the how cloud AI can empower you to build the scalable machine learning development platform. Let's take a look at another aspect of the building a production machine learning system. That is a gap between POC and production. For example, data scientists usually tend to focusing on the sample data, not the raw data. For example, if you have 10 million users, in the process of the prototyping or the POC phases, they don't think about building an optimized platform for supporting 10 million users. But there will be a gap between the POC or prototype and the production system where you have to support the 10 million users with the stable and robust and scalable code. So ops teams have to spend much time and cost for make the POC system much scalable and robust. So these are the gaps between POC and production. Many cases, each notebooks written by the data scientist could be locally dependent or personalized to a certain person. Instead, in production system, you have to make everything portable and shareable. And a single notebook instance cannot support the 10 million users. Instead, you always have to have the multiple instances running on the scalable infrastructure with some auto-scaling out, auto-scaling in features with the load balancing. Any incoming request should be dispatched with the load balancing algorithm. And also, you cannot depend on the fragile manual process. Instead, everything should be automated and reproducible with the end-to-end lifecycle. Lastly, you have to think about monitoring. With the production system, data scientists cannot be sticking to the system for 24 hours or 365 days. So the data scientists have to build a continuous monitoring system working with the ops teams for the continuous alerting and continuous monitoring to make sure that machine learning model keep providing the benefits to the users. And another product I want to introduce here is the AI platform prediction. This is another managed service in the AI platform for the online or batch prediction. AI platform prediction provides the auto-scaling feature based on the traffic load. So you don't have to think about how many instances or servers you have to run to handle the incoming traffics. Based on the traffic load, it can be automatically adding more and more instances or reducing the number of the instances. And also, you can log everything to the BigQuery, the data warehouse service on Google Cloud. So you can easily set up the monitoring system with BigQuery and logs recorded on BigQuery. The AI platform prediction supports the NVIDIA T4 GPU, which is the best the GPUs for the prediction use cases. And everything is running on the Google Kubernetes engine or GKE. And usually, if it's not a managed service, you have to have the ops teams to work with the GKE to build the scalable infrastructure for the machine learning system. But because this is a managed service, the ops team don't have to spend much time on building their own systems. Instead, it's running on GKE, but it's managed service. And many things are taken care by Google. So let's take a look. Let's take a look at an example how the engineers, ops teams, data scientists can work together on a scalable platform. This is a demo video runs on Jupyter notebooks, and initially data scientists would start using the notebooks for building the usual machine learning model. In this case, it uses the scikit-learn for building any simple model. In the first part of the notebooks, it loaded some the results set from the query from BigQuery, and then it reads the results set into the data frame, pandas data frame, and use the scikit-learn to build a simple pipeline for the machine learning training. So this is the usual process the data scientists would take on the Jupyter notebook. So it's a usual the scikit-learn data science process. And then you can export the trained model of scikit-learn to the Google Cloud Storage so that you can share the trained machine learning model with the ops engineer. Ops engineer can use the gcloud command to register the model to the Google Cloud Prediction service, so that now it can be used for the prediction service at scale. Because it's a managed scalable service running on GKE, it can take many numbers of the incoming requests. So as you can see, you can easily share the same notebook with the data scientist and ops engineer to build a scalable production system with Google Cloud. Another component we can introduce here is the deep learning containers, or DLC. It's a standardized container image for data scientists. So actually, the software stacks used in the DLC is exactly the same as the software stacks used in the DLVM. So difference is the VM or container. So why container? Because using the container technology or the container environment like a GKE, the ops team can easily migrate the existing the machine learning softwares or the models to the scalable container-based infrastructure without spending much time on rewriting the TensorFlow code and so on. So by using DLC, you can easily get all the benefits you could get with the container environment, such as GKE. Those benefits include the scheduling or lifecycle management or scaling, load balancing, logging and monitoring, troubleshooting, and so on. As you can see on the animations, you have to think about how you can dispatch each incoming request into the appropriate pods of the container environment, or you have to think about how many pods or how many instances you have to handle those incoming requests and so on. But those features are already installed on the container environment, such as GKE. So you don't have to build everything from scratch. This is a typical use case of the AI platform combined with the other cloud the tools, such as the BigQuery or Google Cloud Storage and Google Cloud Dataflow. So in many cases, for the ETL or data ingestion or pre-processing phases, many people are using Google BigQuery, the data warehouse, or Google Cloud Storage and Google Cloud Dataflow for the batch processing or stream processing of the ETL on data ingestion. And then use the training data with the AI platform training for the scalable training. After finishing the training, you can bring the trained model for the serving platform. The model could be shared on the Google Cloud Storage, and you can use the AI platform serving, AI platform prediction for the scalable serving. So let's take a look at another scenario that requires, that talks about the gaps between POC and productions for the performance issue. So data scientists usually is not required to optimize their notebook code for getting the best performance for the production system. So maybe the POC notebook can support the 10K rows, but in production system, sometimes you have to handle the 10 million rows and train the model like every day or every hour. How to build that pipeline? One solution could be TensorFlow Enterprise and its cloud storage and BigQuery reader. The difference between the TensorFlow and TensorFlow Enterprise is that TensorFlow Enterprise is a commercial product provided by Google Cloud with the technical support. And the TensorFlow Enterprise is fully optimized for the runtime performance with the other Google Cloud products, especially the I/O performance with the Google Cloud Storage and BigQuery is highly optimized compared with the open source version of the TensorFlow. But as a data scientist, you don't have to change anything, almost anything on your existing TensorFlow code. As you can see, all you have to do is specify the green part, the URI of the Google Cloud Storage dataset with gs://URI. So that the TensorFlow Enterprise automatically detects that this is data that sits on the Google Cloud Storage, so that it uses the optimized binary code for getting the optimized performance with the Google Cloud Storage for piping the data into the training part. You can get the same optimization benefit with the BigQuery reader as well. As you can see, there's an API for the BigQuery reader that could be easily used in the notebook so that you can easily execute a query on the BigQuery and get the result set from BigQuery and read it with the multiple parallel threads at high performance. What's the performance, the difference? This is a comparison graph compared with the TensorFlow Enterprise and the open source version of the TensorFlow with the previous version. The difference is almost, 2 times higher than the open source version. And that means you can pack much more training data to GPUs, and you can get the higher GPU utilization ratio, as you can see on this graph. So we were able to observe almost 30% increase of GPU utilization with P100 GPUs. Another benefit you could get with the TensorFlow Enterprise is the technical support. With the open source version of TensorFlow, there's no commercial technical support you can get from Google. But with TensorFlow Enterprise, you can get up to 3 years of the commercial support for each supported versions, such as 1.15 or 2.1 or 2.3. So you can open and ticket with the standard Google Cloud support program and ask any questions or ask for some solutions for the problem you would face with the TensorFlow. So it's a commercial product. Next, I'd like to discuss about how the data and model validation is important and how you can solve these problems with TFX. These problems can be seen in the anti-patterns. One of them is the lack of data validation. So with machine learning, actually you are building an IT system, but the core part of that IT system is replaced with the machine learning models, rather than using the ordinary traditional programming code written by humans. In the usual IT system, the ordinary IT systems, the people, like the programmers, would be writing all the logics and business logics and the code with Java or Python or C. And usually they write millions of the unit testing code to make sure the behavior of the system is, is working as expected. But with machine learning, the core part or core behavior of the system is defined by the data and the machine learning model. How you can make sure that your behavior of your system is working as intended? Because there's no way to write the millions of the unit testing code against the machine learning system. So this is the big pitfall you would face with the production machine learning system. Now, data is new code, but there's no proper way to make a validation of the system's behavior. Another anti-pattern you would face with the production system is the training serving skew. In many cases, training time, the data scientists would use the provided training data. But in many cases, in the production system or the serving system, the model will face with quite a different data with the different the distribution on each features and so on. And any differences such as the distribution in each column or in a feature of the serving data, or the way they do with the processing, how to define the window for the stream processing and everything, those can be a cause for the skew. You drop down the accuracy you're seeing with the serving system. The one solution we provide is the TFX, TensorFlow Extended, which is an open source tool provided by the TensorFlow team. And now the yellow part, such as data validation, model analysis, and pipeline, and so on, orchestration, those are published as an open source tool. So anyone can go to the tensorflow.org/tfx and download the tool and use it right now. So it's an open source tool. So you don't have to pay anything for start using TFX, but it provides the significant values that is learned by Google for in last over 10 years. TFX is kind of second generation of the CBO, which is the proprietary production machine learning. What is that? Production machine learning, the deployment and the development platform for Google, used by the many largest machine learning-based services such as the Google Play and Gmail and so on. And with those learnings and experience with CBO, we built the framework that is called TFX, and we open sourced the source code. So it's now freely available. One of the components included in the TFX is TensorFlow Data Validation, or TFDV, that helps developers to understand, validate, and monitor their machine learning data for the training at scale. And actually, TFDV is already used by the many largest projects in Google, including the Google Play team and the YouTube team, with the petabytes of data at Google every day. So it's a proven technology. And this is a quotation from the TFX paper. Why we spend so much time and cost for building a data validation system? Because they want the user to treat the data errors with the same rigor and care that they deal with the bugs in code. So any unexpected distribution or the patterns in the training data could be just like a bugs you would find in your programming code. Actually, Google Play team was able to introduce the TFX so that they were able to increase the application install rate, improved for 2% for the average of the whole applications they have on the Google Play platform, just by introducing the data validation and finding a state table. So let's take a look at how it works. And because it's an open source tool included in the TFX, you can just use the usual Jupyter Notebook environment, as you can see on this video. In this demos, initially it executes the query on the BigQuery to get the Chicago taxi logs with all the features such as the fares and what is the credit payment types and so on. And you can use the TFDV for digging into the statistics values you can see on the training data. And you can easily click on the UIs to dive deeper into each features. In this case, what are the major payment types the customers are using? Is it cash payment or is it a credit card payment and so on? And you can also easily compare the distribution or statistic values between the different data sets, between the training data and the variation data. Sometimes data scientists would see the different accuracy or metrics you would get with the training and variation. But in many cases, that is happened because of these difference of the distribution or the statistics in the different data sets. And you can easily visualize those differences. And also, TFDV allows you to find the different skews between those different data sets, like training and validation and production. So you can use the TFDV tool to set up some kind of the trigger that is triggered by those drifts and skews, like changes of the distribution in each feature. Another anti-pattern we would see in the production machine learning system is not knowing the freshness requirements. And the freshness requirements would be different based on the business requirement. For example, news aggregations site or service would require to retrain the whole model every 5 minutes. Or maybe e-commerce recommendation system only need to retrain the model every day or every week. Whereas the other applications such as the natural language processing or the voice recognition maybe don't require much frequent the retraining of the model. So it's totally depending on the business requirement, and you have to define that before starting and designing and building the machine learning systems. So this is an important rule that is defined in the ML paper, machine learning paper that is published by the Google. You have to know the freshness requirements of your system. The one solution that could be used for to solve this problem is the TFMA, or TensorFlow Model Analysis. This is a tool for evaluating the metrics of your trained machine learning model. And you can specify any quality thresholds like accuracy or any other metrics. And you can make sure that your model is working as intended. For example, the easy way to use the TFMA in production is to compare the models with the timestamps. So not just taking a look at the accuracy number with the latest model, you have to you may want to compare the different accuracy number from the different timestamps. For example, maybe 1 month ago, this model's accuracy was like this. 1 week ago, this model's accuracy was slightly dropping down. And today, the model's accuracy is significantly dropping down. And you have to notice that by visualizing or measuring those metrics. And also, you can define any slice. Slice means different segment of the data sets. And not only the timestamp, but also you can define any different dimensions as slices. For example, you can define the slice as, like, for example, demographic attributes, like the location of the user, whether it's a user in Japan or user in the United States, or maybe age group, whether the performance is for the younger person or elderly person, or maybe between the different the identity groups in the users, so that you can take a look at the difference of the accuracy or other metrics between those identity groups. Maybe it's possible that your model is working so well for the people in the United States, but it doesn't work so well for the Japanese people. And you can detect that by defining the slice with the TFMA. So let's take a look at another video for the TFMA and how it works. So again, it's just an open source tool provided with TFX, so you can easily import it on your usual Jupyter notebook, like this one. And you can define some of the metrics and you want to monitor with TFMA, so that the TFMA start evaluating the different slices, and it tries to visualize the difference between those slices. In this case, it defines the timestamp as slice. So you can easily see the differences between those metrics based on each timestamps. Maybe the model works so well in the daytime, but you can notice that the accuracy will be dropping down in a certain time of day. So that with the machine learning production system, you can set up some trigger and alert for the ops teams to get alarm for the accuracy dropping. Lastly, I'd like to discuss how you can build a machine learning lifecycle management platform. Because in the early days of the data science, many the notebooks or the Python code written by the data scientists are so fragile. It's totally dependent on the manual fragile process and dependent on each data scientist person. And maybe you could get the model with higher accuracy, and you can push that model to the production system. But after many years, maybe a couple of years or 5 years, people would forget about the system. And then you would get some emergency alert from the production system that is built like a couple of years ago. But if you don't build a machine learning pipeline with the proper machine learning lifecycle management with the ops team and data scientists and ML engineers, then the one person, the superhero, the data scientists have to take care of everything, like emergency planning. Why they have to do that? Because they didn't think about how to rolling back the trained model to the previous model or things like that, backing up, scaling out, everything. This is all about the problem solving for the machine learning production system. So that's the reason why we introduced a new product called Cloud AI Platform Pipeline. That is a product for the ops engineers, mainly for the ops engineers and also for the data scientists to build a production machine learning pipeline just like the combining the log blocks for building your house. So we provide the multiple different components and modules, so you can easily build your own pipeline with those modules. And this is the system diagrams of the AI platform pipeline. Inside it, actually, we are using the open source Kubeflow pipelines running on the GKE, Google Kubernetes Engine. And we provide it as a managed service. So again, you don't have to spend your time to prepare for the GKE instances or pods and everything, and install the Kubeflow pipelines open source tool by yourself. Instead, you can just click some buttons to build your pipelines that is managed environment. And also, as you can see on the diagrams, you can easily use the TFX tools, such as the TFMA or TFDVs, combined with the other pipeline tools. And with Kubeflow pipelines, you can easily visualize what is happening in your machine learning pipeline with the DAZ, directed acyclic graph. So you can just click each one of the rectangles or blocks so that you can check out what is happening right now on the pipeline. Let's take a look at another video how it works. So on the user interface, you can easily click one of them to look at the status of each system. This is the basic the functionality it provides. And also, it provides the artifacts management features. So artifact is anything you would get with the data preprocessing or data model training. So preprocessed data set or the trained models and so on, they are managed as artifacts so that you can apply the lineage management like this one. So it's important to manage all the lineage between the data sets, hyperparameters, and model design and so on, so that everything can be reproducible rather than dependent on the humans, the memory or data scientist practice and so on. So summary, we have talked about what is machine learning ML ops and why it is important. And we introduced the cloud AI tools, especially the AI platform and TensorFlow Enterprise, for building a scalable machine learning development systems. And also, we have discussed about what are the gaps between POC system and production system, and how you can build with the different tools from the AI platform, such as AI platform prediction, AI platform training. And also, data and model validation is so important for the ML ops system, because it's just like writing a unit test or regression test for the IT system. Lastly, with the AI platform pipelines, we showed that you can easily build a machine learning lifecycle management. So that was it. Thank you so much.